I haven't published since I turned it in. And I kind of messed up on it to it.
What's good? How are y'all?
Good.
Great.
Pretty good.
Good. I was almost late to class today. I got to ride the bus with maybe a whole school full of middle schoolers. It was kind of wholesome. There was like this one kid who's like, I can't wait to play saxophone in the recital.
Wow.
That's put me in good spirits. Also, my Braves are playing today. That's kind of stressing me out, but I'm also, this is kind of a long lecture, so we're not going to get back in time, but that's okay. First things first, do we have any housekeeping kinds of questions? Any lingering questions from last week? That kind of thing.
I have one question about mutate.
Okay.
I was having trouble in the slides, the way you had it, it was like within types, and then I could get to work. But if I just tried to do like mutate and like the data set that I had, it would run it. But then when I would look at the data set, like the new column wouldn't be there. And I didn't understand if that was you can't do it by itself.
Yes, you can't do, the question was, I've been doing mutate and I put the data inside of the thing rather than piping it in. Why is my column not staying there? It would if you saved it to a new object. This would create another data frame that includes your column.
Okay.
Question in the back. Yes, certainly. Because if you want to just keep it, I was doing an example earlier. Sorry for the people who are watching this recording. I'm going to draw. Can you see this little square here? Okay, this is an R script for a markdown. And let's say we have our YAML up here. Then we have our first chunk where we would load all our libraries and our data. Next chunk for me, almost always, is creating all of my columns that I'm going to be using throughout the entire analysis. If it's the case that I'm going to do adding columns and things within the markdown. Very rarely do I do this, but if that's what I'm going to do in a markdown, this is how it goes. Normally what I do is all of my data cleaning and making new columns and things is in an R script by itself. I then save that CSV and then load it into my markdown to make the plots. Cool. Okay, this week we're talking about data structures, and you're caught. You're stuck. It's too late. This week is a bunch of jargon and computer words, and you don't get to make fun graphs. I know, but I wrangled you in. It's too late. R data types. So far, we've been manipulating data frames, making visuals, and summarizing, and this has got you pretty far. If you recall what it was like a month ago, if someone asked you, what can you do in R? You'd be like, But now you can make cool plots and make little reports and things and think about how you're gonna summarize data, manipulate data frames, what have you. Now we're going to get more into the weeds of programming. So today is all about types of data in R. Thus far, we've worked a lot about how to do certain things in R. And today we're going to try to cover some of the why we did some things in R, the way we've done them so far. Also, I said I'm going to say a bunch of computer jargon and R coding things. Stop me when I say some weird word or phrase that you're not familiar with that has to do with computers. So up until now, we've worked with data frames, basically exclusively. And I've been describing data frames as like kind of a group of vectors to some people, when a data frame is really a list of vectors, where every vector is a column of the same length. So this is what our number of rows is. Every column is a vector with the same amount of elements in it. But data frames are not the only object we want to have in R. For instance, a linear regression output object, very common, kind of what we want to use R for. But we also need to learn about vectors, matrices, and lists to do additional things that we can't necessarily express with dplyr syntax. We're going to start with vectors. Vectors are great. We've done a lot with vectors so far, but we're going to talk about them specifically unto themselves. In R, we call a set of values of the same type of vector. We can create vectors using our concatenate function. For instance, this vector here has the elements 1, 3, 7, and -0.5. Vectors have one dimension. They're only long. They're not tall. They're just long. They're not fat. They're just long. So this vector, for instance, has 4 elements. All elements of vectors are the same type. I don't know if you've noticed this yet, but when you're dealing with a vector, it's either all numbers or it's all strings. It's all characters. If you mix character and numeric data, the resulting vector will be character. The reason this is that we don't want to lose information. If it converted, let's say we had a vector with the elements 1, 3, and the word yes, and it converted yes into a number, we would lose information about how humans interact with text. I would say that character is sort of the least common denominator when it comes to accepting elements of a vector. One thing that's really great about vectors is that you can do element-wise vector math. Yeah. When doing arithmetic operations on vectors, R handles them element-wise. For instance, we have a vector here, 1, 2, 3, and then another one, 4, 5, 6. And if we just add them together here, we'll get the answer a vector of 5, 7, 9. So what happened was 1 got added to 4, 2 got added to 5, and 3 got added to 6. We can also, let's say we want to do one operation. We want to take our vector to the 3rd power. And we'll do this for each element. So 1, 2, 3, 4 to the 3rd power will be 1, 8, 27, and 64. This is really great because now when we're dealing with vectors, we can manipulate them all the way across and still receive a vector back. Some common operations you might want to use: multiplication, division, exponentiation, taking the log of things. These will all be done element-wise on a vector. If we work with vectors of different lengths, R will recycle the shorter one by repeating it to make it match up with the longer one. So let's say we have a vector with 0.5 and 3, and we multiply it times a vector with the elements 1, 2, 3, 4. What will happen is R will multiply 0.5 times 1, 3 times 2, 0.5 again times 3, and 3 again times 4. And we'll receive a vector back of 4 elements with all of these calculations. This is the same thing as multiplying 2 vectors where 1 is the elements 0.53, 0.53. We can also recycle scalars. A special case of recycling involves arithmetic with scalars. This is a single number. If you are familiar with other coding languages, scalars might be slightly different. In R, they are a vector with one element. Here, we have 3 times a vector with -1, 0, 1, and 2, plus 1. And note that R obeys the order of operations. It does multiplication and division before the addition. So we do 3 times -1 plus 1 to get -2, 3 times 0 plus 1 to get 1, 3 times 1 plus 1 to get 4, 3 times 2 plus 1 to get 7. You can use parentheses to control the order manually. Let's say you wanted to add 1 to all of these elements of the vector and then multiply by 3, for instance. A warning on dealing with recycling of vectors. Recycling doesn't work so well with vectors of incommensurate lengths. So let's say we have vector with 1, 2, 3, 4 as its elements, plus a vector with 0.5, 1.5, and 2.5. R will kick back an error if you try to do this analysis. It'll say, warning in both of your vectors, longer object length is not a multiple of shorter object length. This is very instructive. I find that R a lot of times sends you an error where it's hard to understand what they're trying to tell you. But when you get one about different object lengths, at least you know where to start. It's probably a recycling issue. So try not to let R's recycling behavior catch you by surprise. Do we have any questions so far about recycling? Excellent. We can also do vector-wise math. So earlier we were talking about element-wise math. Here it's vector-wise math. Some functions operate on an entire vector and return one number rather than working element-wise. For instance, we could take the sum of the vector 1, 2, 3, 4 and get the number 10. Same thing for max, 1, 2, 3, 4, we'll get 4. Some others, min, mean, median, standard deviation, variance. You've seen these when we were using dplyr summarize. And when I described it then, I said, it takes all of the rows and returns you back a calculation about them. But really what it was doing, it was looking at the vector that your column is and returning back a single calculation about the entire vector. Oh, that reminds me. I got the most delightful question on the Slack the other day. Somebody wanted to get a bunch of statistics like this for the flights data set using like mean, median, min, max, etc. And group them by like, or take the flights, group them by carrier, and then get all of those statistics for them for the times. And at first blush, I was like, okay, sounds pretty good. I could just group by carrier and then summarize to these things. And then I realized that the departure times is actually in like hours and minutes. And so if you take an average of hour-minute numbers, you'll get nonsensical things like 1297. And so it took quite a while to get the numbers to get converted to seconds and then do it. Highly recommend checking out that Slack. I'm very proud of my answer.
You just divide the data in each cell to make it whatever. Like, no?
Yes, I took the column, the departure time column, and then converted it to seconds.
Yeah.
First. An example that uses both element-wise and vector-wise calculations is, let's say we want to get the z-scores of some test scores. And we want to put these on a standardized scale, right? That's what I mean by getting z-scores. If you've got no stats training, what I'm saying is I convert test scores into a unit that's comparable across all of them. So let's say we have a vector. We're going to assign it to the object X of some test scores. And then we want to make an object Z. We're going to assign it our vector minus the mean of our entire vector divided by the standard deviation of our entire vector. And then we'll round it and make it look nice, okay? What we'll get back is a vector of the same length as X in standardized Z-scores. And the way that this works is exactly what it says here in this math. For each element, so this I, for each element in our X vector, subtract the mean of all of the stuff in X, divide by the standard deviation of X, and then we'll get back a Z-score per element. Also, if you're down with stats, this is just the scale function, but I wrote it out so that we can see how element-wise and vector-wise functions can work together. Do you have any questions there? Great. So there are quite a few types of vectors. You can check what type of vector that you have using the class function, the type of function, and the structure function. Here are a few types. We have numeric data. Here are just numbers. They can include decimals and fractions. And in fact, you can just put calculations inside. So here we have 1, 10 times 3, 4, and negative 3.14. We have integer data. These are just whole numbers. And it's important that we know when we have an integer rather than a basic numeric. Integers are a subclass of numeric. We also have characters, things like red, blue, yellow, blue. These are strings of text. We also have factors. Factors are categorical variables that are either numeric or a string. You'll note that if you wanted to run a statistical model on, let's say, red, blue, and yellow, R would need to convert them to a number in order to do the assessment. This is what factors are. Things like Likert scales are also factor type variables that we're very familiar with. On a scale of 1 to 10, how dissatisfied are you? Great. Do we have any questions there? Yes. Right. Yes, we'll be covering how an NA works within a vector in like 10 slides maybe. But suffice to say that one NA will spoil the broth. If you have a list of things and one of them is missing, it's hard to try to get the average of it.
Okay, but I already got rid of the.
You got rid of the NAs.
It still it won't work, but so I put as in my request. I was wondering why it works.
I see. I don't know off the top of my head. Can you send me that like code chunk? I'm really interested to know. We also have logical types of vectors. These are just false and true. This is the setup of how our filter function works when we want to get rid of rows. a point about generating numeric vectors. Numeric vectors contain only numbers with any number of decimal places. There are shortcuts for generating common kinds of vectors. You could use the sequence function. This will take a starting value and a stopping value and other arguments to create a vector of a numeric vector. You can also use REP for repeat. Here you can repeat a vector as many times as you like, so you can supply an amount of time, or you can supply each and it will repeat each element. So here we have the difference between element-wise and vector-wise again. I also wanted to show something about sequence because I couldn't quite get it to fit in the slides. I very rarely use sequence for sorry. I very rarely use sequence with the by argument. I often use it with the length.out argument. So if we run this, we'll see that it goes from -3 to 6 in increments of 1.75. I often find it much more useful to use length.out and say like 10, because the amount of character or the amount of elements in my vector for vector-wise kinds of math is often more important than the distances between the elements. So just something to note. We can also generate integer vectors. Integer vectors are a special case of numeric vectors where all the values are whole numbers. We can produce them using the colon shortcut. So let's say we create an object called n and assign it the number 12. We can say 1:n, and we'll get a vector with all of the digits 1 to 12 as whole numbers. We could also say n:4, and it will go from 12 down to 4. One interesting thing about this is that it creates integers, but if your initial object is not an integer, it will still go that distance, but it will retain the decimals. I'll show you what I mean right here. So let's say to n, we supply 12.6, and then we say n to 20. Here, it just adds integers to all of the elements. You can also specify a single integer using a whole number followed by a capital L. It might not be immediately obvious why you would want this instead of just a number 9. I often just use the number 9. There are very few functions where it's going to ask you for an integer back, and this is how you would tell it. This 9 is an integer and not 9.0000. All right, on character vectors. Character vectors store data as text and typically come up when dealing with names, addresses, and IDs, and virtually all the data sets I work with. So let's say we create a vector with the elements Andre, Beth, Carly, and Dan, and the class of this object called first names is character. Note you can store numbers as character data as well, but you cannot perform math on them unless you convert them to a numeric. One such example would be 3 plus 5. Doesn't work. As dot numeric, 3 plus 5 works. So factors are categorical data that encode a modest number of levels So I talked earlier about the Likert scale having like 1 to 10. Each of these numbers would be a level. These are often things like sex or experimental group or geographic region. Let's say we have an object called sex, assign it factor, a vector with M, F, F, and M. And then when we look at the sex object, the levels are also specified. You might have noticed in the Gapminder data that some things were also of this kind. I can show you. So if we did structure Gapminder, country is a factor with 142 levels. Continent is a factor with 5 levels. And in fact, it's if you pulled it out as a vector, so let's say we said Gapminder pull, you'll recall pull, continent. And we could say as that numeric, so we could see all the numbers. Goodness. It'll just tell you all of the numbers in the data set, even though when you looked at it and worked with it, it was all text. Character data usually can't go directly into a statistical model, but factor data can. It has an underlying numeric representation. Note, most R models will automatically convert character data to factors, and the default reference is chosen alphabetically. Keep that in mind. The default reference is chosen automatically or alphabetically. Logical vectors take only true and false values and are typically the product of logical tests. So stuff like x equals 5. We can make logical vectors by defining binary conditions to check for. For example, we can look at which of the first names has at least 4 letters. So we'll make a vector called name, or make an object called name lengths, assign it the function nchar, which is just counting the number of characters in first names. And when we check out the name lengths vector, we get 5, 4, 5, and 3 for Andre, Beth, Carly, and Dan. When we use it, the vector within a logical expression, something like name lengths greater than or equal to 4, it will return a logical vector. Andre has a name that's greater than or equal to 4. Beth has a name that's greater than or equal to 4. Carly has a name that's greater than or equal to 4, and Dan, unfortunately, does not. Logical vectors also have an underlying number. You can do math with logical vectors because true is equal to 1 and false is equal to 0. So we could say with our logical expression, name lengths greater than or equal to 4. If we take the mean of that logical expression, it produces 0.75. So what does this last line do? It told us the proportion of name lengths greater than or equal to 4. This is really great. By this same logic, it's really easy to count or estimate how many NAs you have in your column, for instance. So let's combine logical conditions. Suppose we are interested in which names have an even number of letters. So we take our name lengths vector, and then we use the modulo operator. This does division, but hands back a remainder. And we say, after this division, is the remainder equal to 0? And we assign it to the even length object. And for our name lengths, which were 5, 4, 5, and 3, even length is only true for Beth. Or let's say we wanted to know for which names is the second letter the letter A. So we assign to our second letter A object. Here I use the substring function. This lets you cut down text using the length of the text. So I use substring on the first names, and I start with the second character and stop on the second character, and then test if it is equal to the letter A. And that's not true for Andre and Beth, but it is true for Carly and Dan. And now, when we use logical operators like the ampersand, the and, both conditions must be true to return a true. So if we said even length and second letter A, all of these things would be false. If we use the or, at least one condition must be true to return true. Andre is the odd one out. Beth, Carly, and Dan are true. Note that the exclamation point is the negate. Here, the not switches true and false. So if we said not even length or second letter A, we'd receive just Andre is true and all the rest is false. Do we have any questions there? Yes, so here the modulo is dividing element-wise this vector by 2. And it does division and then hands back a remainder as its output. And then the test on equals equals 0 is saying, is the remainder equal to 0? We can subset a vector in a number of ways. We can pass a single index or vector of entries to keep. For instance, we can take our first names object and subset with these single brackets a vector with the 1 and the 4, and this will provide the first and fourth element of our vector. One thing you might note here is that I have to know what the first and fourth element of the vector are to subset using this manner. You can also pass a single index or vector of entries to drop by including a minus here. This is very similar to the syntax that we used in the select function in dplyr. We can subset vectors by passing a logical vector where true equals keep and false equals drop, and actually include multiple vectors the same way we used that expression before. So if we said first names subset by the expressions even length or second letter A, we would receive back Beth, Carly, and Dan. We could also subset by logical expression that has commensurate lengths of vectors. So here, first names subset by sex not equal to F. And what we receive back are Andre and Dan. Have any questions there? A little bit about some logical and subsetting functions. So we've talked a little bit about percent and percent before, and how it lets you avoid typing a lot of logical ors with the bar. Something like first names, percent and percent, Andre, Carly, and Dan. This will provide us with a logical vector, true, false, true, true. Question?
Are you always just working with one vector at a time? So whatever you're like, the functions, the commands that you're doing, you're always just referring to that one. So when you're done with that, like when you do C brackets, it's only on the current one. So then like whatever you were doing above that doesn't matter.
You're asking if the
Like,
comparisons that you made before, like earlier,
yeah, like if you had
stick
made
around?
vectors before,
Mhm.
but now you're like on a separate one, you can always just only work with one vector.
I'm a little bit confused because
Maybe
if you
I-
wanted to work on like many vectors at the same time, then you're working with the data frame.
Okay.
Question in the back. Yes, I think the answer is yes. I can't currently think of a counterexample. Okay, the which function gives us the indices of truths in a logical vector. So we could say which first names, percent and percent, are Andre, Carly, and Dan. So this is how we would get those elements that we're interested in. Recall earlier, I was like, how am I supposed to know for a different vector what elements I want? I just put in 1 and 4 because I already knew. But here, we can use which to get a vector with the elements of interest for their indexes. On missing values. Missing values are coded as NA, all caps, entries, and they're not in quotes. So we can make this vector here, vector with missing, which has the elements 1, 2, NA, 4, 5, 6, NA. Even one NA will poison the well. You'll get NA out of your calculations unless you remove them manually or with an extra argument, such as na.rm equals true, which is available in some functions. I know a lot of people ran into this question for the homework with trying to get the average. Note that this is a special kind of element and that it's an element that's not there. Like it's something that's missing. It's something I always try to keep reminding myself that it's like it's empty and that there's nothing holding its place. Warning about finding missing values. You can't test for missing values by seeing if they're equal to NA. For instance, we could have a vector with missing equals NA, and it will just always throw back NAs when you try to do this because it's poisoned the well. Instead, use the is.na function. Is.na will provide you with the logical vector telling you where NAs exist in your vector. And you can do things like take the mean of the vector with missing, subset to is not is.na. So we've flipped the true and false values here so that we keep only things that are not NAs. Note this is the same as mean of some vector na.rm equals true. Do you have any questions there? I know NAs can be a little bit weird. Question? Sure. So what's happening in this code here is that I'm subsetting to things that are not NAs. And the way I'm doing that is using the exclamation point to flip true and false on the is.na function. And so it only keeps the things that are not NAs. And then tell me the average of that. Great. Something to note about NAs and comparing them to things. When testing logical conditions, NA will produce NA rather than true or false, as we showed in the last slide. It's noteworthy, however, that percent in percent will handle NAs. So you could, for instance, say vector with missing percent in percent 5, and it will just say it's false for the NAs that we had, or percent in percent NA, and it will say true for the NAs that we had. I don't recommend doing this. Because more often than not, when you have social science data, NAs are like valuable information that you need to think seriously about. And so really think about what happened at the data collection stage and what an NA means to the column type before you just start dropping them or using them in logical expressions like percent and percent. I included it here so that you knew what it was, but I'll say that I don't do this ever. A little bit about INF and NAN. Sometimes we might get positive or negative infinity. This will be represented by capital INF or negative capital INF, or NAN, which means not a number for our calculations. So let's say we have this vector -2, -1, 0, 1, and 2, and we divide it by 0. We'll get negative infinity for the first two elements, not a number for 0 divided by 0, infinity for 1 and 2. This doesn't come up a ton in my own work, but I want you to know what it is. You can check for these by using functions like is.finite or is.not a number. On this same vector, you can see that is.finite is false for every element here, and is not a number is true just for 0 divided by 0. Can I test something real quick? It just struck me. I think that pi is like a saved thing. Okay. For some reason, I thought pi was a saved thing with like many, many more decimals, and I wanted to check if it was finite, but it only goes to 7 places, it looks like, so never mind. So we can preview vectors like we had with data frames. We can use head and tail to preview vectors. So we could say head letters. Note that all undercase letters, the word, is a built-in vector in R. That's just the English alphabet A to Z. We could say head letters 10 to produce the A to J vector, or tail letters for the last 6 elements, U to Z. We can also index vectors by assigning names to the entries. So let's say we make a vector with the numbers 1 to 26. Question. I don't know. We can also index vectors by assigning names to the entries. So let's say we make an object, a vector, and assign it the numbers 1 through 26 as whole numbers. Then we can apply to the names function. We can assign to it letters in all caps, which is the capital versions of all the letters. And when we look at the first 6 elements of that vector, we'll see our 1, 2, 3, 4, 5, 6, which is our vector, and then the names of each of the elements, A, B, C, D, E, F. This is really great because when we want to subset, and we don't know what position in the vector the things we want to subset are, but we do know what the names are, we can subset by saying, a vector, single brackets, a vector with some letters, let's say R studio, and it will supply back the vector of just the elements we subset without us having to know the position within the vector.
How did it know that root for eight? Like is letters something that R knows the alphabet for?
Yes, it's built into R like Swiss. Yeah, I'm gonna take another sip of water. I hate matrices. Okay, so I don't like dealing with matrices. I avoid them at all costs. That's because I didn't pay attention in linear algebra. Okay, so matrices have 2 dimensions. Recall that vectors just had the 1. Matrices extend vectors to 2 dimensions. The dimensions are rows and columns. We can just construct them directly using the matrix function. Note the by row argument, which determines whether the data fill the matrix by row or by column. So in our first example here, we make a matrix and we assign it the function matrix with the letters subset to just the first 6 letters, with the end row argument taking the number 2 and the number of columns taking the number 3. By contrast, our second matrix, B matrix, by row equals true. And you'll note that if we don't have by row equals true, the default then would be by row equals false. And it fills in the first 6 letters of the alphabet column-wise first. So in the first column, we have A, B. In the second column, we have C, D. In the third column, we have E, F. Whereas in our B matrix, by row was true. So our first row is A, B, C, and our second row is D, E, F. We can also make matrices by binding vectors together with the rbind function. This means row bind, and cbind function, which means column bind. So our C matrix, assign it cbind 3 vectors, the first one taking 1 and 2 as its elements, the second one 3 and 4 as its elements, and the third one 5 and 6 as CSSS elements. And since it's the column bind, our first column will be 1 and 2, second, 3 and 4, third, 5 and 6. In our D matrix, we use R bind, the vectors 1, 2, 3, and 4, 5, 6. And we'll see that they stack on top of each other with 1, 2, 3 in the first row, 4, 5, 6 in the second. We can subset matrices using the same methods as with vectors, except we index them with this format: rows, comma, columns. So let's say we want to get to our A matrix and get the first row, second column cell. We would say A matrix subset with a single bracket, 1, 2, and we'll get C. We can also specify 1 as our row and a vector with columns 2 and 3 in order to get the first row and the second and third columns material, C and E. This is good because the vector-based subsetting still applies. And I want to note with matrices, pay attention for that comma. The comma does a lot of heavy lifting for you. We can obtain the dimensions of a matrix using the dimension function, dim. Note that using length on a matrix will not give you the number of rows or columns, but rather the number of the total elements. But often with a matrix, we're not so interested with the total amount of elements, but rather the rows and columns. So use dimension. For our A matrix, it returns 2 rows and 3 columns. A bit about matrices becoming vectors. If a matrix ends up having just 1 row or column after subsetting, by default, R will make it a vector. This is very sneaky. I don't like it at all. In fact, you can prevent this behavior using drop equals false. So let's say we wanted all of the rows, but just column 1 of the A matrix. It returns a vector with A and B. So it has switched our data type without telling us. So bear that in mind when you're dealing with matrices, that it might switch to a vector without telling you. If you said drop equals false, again, after a comma that specified the row and columns, it will continue to be a matrix and give you back just the column that you asked for. Any questions there so far about matrices? I'm sorry? So what is it that we want to keep from our matrix? ACE, so we want to just the first row.
Like if you wanted the opposite of that, of row 1, all columns.
If you wanted the opposite of that.
So if you wanted row 1, it should be 1.
Right, and if you wanted to drop column 1 and keep the rest of the matrix is what you're asking? Yes, you would do the same thing, but you would specify a number to the first argument and then comma, nothing, comma, drop equals false. That is something to think about though. How do you drop just one column from a matrix? I don't know off the top of my head. Warning about matrix data types. Matrices can be numeric or integer or factor or character or logical, just like vectors. But also like vectors, all of the elements must be the same data type. It does this same sort of lowest common denominator thing, where if you had a matrix with untold of numbers and one character string, all of it would get converted to a character. So let's say we make a matrix called bad matrix, and we C-bind the numbers 1 through 2 as whole numbers, and the letters, all caps, subset to the 14th and the 25th letter. Note that when we do type of bad matrix, it has converted it to character, even though the first two things we gave it were integers. In this case, everything was converted to character so as not to lose information. So I said before that text is very legible to humans and pretty illegible to computers. And so when I read N and Y, I think of it as yes and no, whereas a computer just reads it as some information. They don't assign value to it necessarily. So if it went the other way and it converted to numbers, we would lose that sort of meaningful information that humans would want.
That also true for like factors and numbers. Factors and
I'm trying to think of an example where there's a factor and a character. It would convert that to character as well, I'm pretty sure.
like if you specified that the N and Y were factors,
Right.
it would still give you like talk about the like as type would be all factors or would go characters.
I'm not sure. Let's check. Because I want to say that I wouldn't just assign some levels to the other one, but maybe it would.
If you did the as factor with the letters. Oh, you did.
I did as factor 1 and 2,
For the
but
letters,
you want it for the
N and
letters.
Y.
I don't, sorry. What was your question? Yes, you could say here instead, and y. Maybe not because it's as dot factor. I'm sorry. if I had it without letters. Oh yeah, I guess that makes sense. You could just get rid of this. Yeah, I don't off the top of my head know why it converted that information into integers though. Something to look up. I'm telling y'all, matrices are cursed. Matrices can take dimension names just like our vectors could take names. We can access dimension names or name them ourselves. Things like we use the row names to provide row names to our matrix. So here I've assigned it Candace and Jonquel, and we have column names that we can assign as champion and MVP. And now our bad matrix is 2 by 2 with our columns named and our rows named. And now we can subset based on these names. So here I subset bad matrix with the row as Candace, nothing for the column, so it will provide both of my columns back, and drop equals false so that it remains a matrix. And what we receive back is a matrix that's 1 by 2 and still has our column and row names and the first element or the elements of the first row. Matrices of the same dimensions can have math performed entry-wise with the usual arithmetic operators. So let's say we C-bind C matrix and D matrix. This is just so that we can look at them both on this slide. And then we say 3 times C matrix divided by D matrix. And what we'll get is 3 times the first element, 1. So 3 times 1 times 1 will become our 1, 1 in the new matrix. Then we can do 3 times 3 divided by 2, which will be 4.5, and 3 times 5 divided by 3 for 5, and so on for the next row. And if you did pay attention to linear algebra, you're probably saying, that's not how I'd want to do any sort of multiplication or division with my matrices. You're in luck. So matrix transposition and multiplication. To do matrix transposition, we use T, just T for transpose. As always in coding, if something is just one letter as the function, it's very important. Here we can make the E matrix by assigning it the transpose of the C matrix. And if you're saying to yourself, I don't really know what transpose means, on a matrix along the diagonal, if you flipped it, that is transposition. To do actual matrix multiplication and not entry-wise, like I showed before, although there are some use cases for that, you use percent asterisk percent. And let's say we want to make our F matrix by multiplying the D matrix times the E matrix. It will follow all of the correct rules for multiplying matrices together. Sometimes when these get really big, R gets really upset trying to multiply them together. Bear that in mind. What's the question? With matrix multiplication, the outside dimensions of each of the two matrices are the only things that are returned because of the way that they're crosswise multiplied together. Yes, it'll provide a 2 by 2 because they're 2 by 3 and 3 by 2 respectively. Note that if you are going to pick the advanced option for the homework this week, you're going to want to keep this slide in mind. Moving forward. So to invert an invertible square matrix, you use the solve function. So here we take the G matrix and we solve the F matrix to invert it. We would use this so that we can like create an identity matrix. In fact, I tried to create an identity matrix just below there by doing F matrix times the inverted F matrix, or G matrix. Does anything seem off about these numbers? This is supposed to be an identity matrix that we get here, but some of our values. What do you think is going on there? Right, it's supposed to be zeros on everything that's not the diagonal in an identity matrix. But here we have negative 3.5 times e to the negative 15, or times 10 to the negative 15, and 1.00000000 instead of just 1. Note this is called floating point imprecision. The off diagonals are incredibly close to 0, but they're not actually 0. The reason this happens is because computers, like me, are bad at fractions. And so when it has many, many decimals and it tries to do all sorts of operations, it will get lost in different places because of the rounding. This often happens with really big variance covariance matrices, for instance. So just bear that in mind, that if you want to check if something is the same as a number after many, many calculations, round it. How about, is this the same as very close to this number? Because sometimes the decimals on a computer are just going to hang around in a really kooky way.
But isn't the way to fix that to go into your data and round the data to the second or third decimal, or without mess up the accuracy? You know, to get rid of some of the things that, you know, like.
Right. That would work in a lot of cases, but when it comes to things that output as a matrix that you didn't get to decide when the matrix gets created, then you would want to round after.
Okay.
We can get diagonal matrices to extract a diagonal of a matrix or make a diagonal matrix. Usually the identity matrix is all that we're interested in. We use the diag function. For instance, we could say diag 2, and we'll get an identity matrix that's 2 by 2. Or we could say diag of the G matrix, and we'll get just 1.7 and 0.6. The reason that we would want to do this, I think most importantly for us, is to get the diagonal of our variance covariance matrix. Very rarely do I need to do that because there's so many other functions where I can get my standard error some other way, but this is how you would do that. If you haven't taken any stats classes and you're like, what is this guy talking about? I'm talking about stats. Okay, that's done. I don't really feel like talking about matrices anymore. But I love to talk about lists because lists are cursed. So what are lists? Lists are an object that can store multiple types of data. So note with vectors, we had It all had to be a character, or it all had to be numeric. And the same went with matrices. It all had to be an integer. It all had to be character, what have you. With lists, they can take any data and multiple types of data. So here I've made a list using the list function, where the first element of the list is a vector that I'm naming first thing, that are the integers 1 to 5. The second element of my list, I'm calling second thing. It's a matrix of the numbers 8 to 11. That is 2 by 2. The third thing is the entire output of a linear regression of distance and speed using the cars data set. And this is all in my list. To access the list elements, you can use its name or a number inside of double brackets. Or you can use the $ extraction operator followed by its name. For instance, we could say my list double brackets first thing, and we'll get that vector of 5 elements. We could say my list extract first thing, and we'll get that vector of 5 elements. Or we could say my list double bracket number 1, meaning the first element of my list, and we'll get the same vector. And you're probably saying to yourself, why 2 brackets? If you use single brackets to access list elements, you'll get a list back. Double brackets will give you the actual element as whatever data type it is, stored as in that location in the list. So if we said structure my list and subset to just with a single bracket to number 1, it would be a list of 1 with first thing is its name, it's an integer vector with 5 elements. Whereas if we said structure my list double bracket 1, we get the actual element as it is stored. So we get the vector of 1 to 5. Note, you can only select a single element at a time using the double brackets, because this would have returned multiple objects. And I don't know if you've noticed yet, but R can only return one object, or R functions can only return one object at a time. Otherwise, operations like assignment would be virtually impossible. Hadley Wickham put out this really incredible photo to explain how the double brackets work in lists. So let's say we have this shaker with a bunch of packs of pepper inside. This is going to be our list. If we subset to just the number 1, we would get our element, just the pepper packet, but still inside of the container. If we double bracket and get the 1, we'll get just the element that we asked for, just the packet of pepper. And if we chain double brackets together, we'll get what's inside of that container, which is the pepper. Who keeps their pepper like that? Note that subsetted lists can be of greater than length 1. You can use vector style subsetting to get a sublist of multiple elements. So here we say my list and subset to the elements 1 and 2 with single brackets, and the length of that will be 2. The structure of my list, where we subset to a vector with 1 and 2 for just the first 2 elements of my vector, will be a list with the first thing and the second thing from before. Do we have any questions there? Okay. Note that regression output comes out as a list in R. For instance, if we look at the structure of the third element of my list, we'll see that it's a list containing 12 elements itself. Yeah, it's a list of a list. And that it has all of this information and that it's really difficult to read as is. Often what we want to do is check the element names within our list using the names function. So names will give you a vector of list element names. So instead of having to look at this and say, I'm not quite sure what my fitted values are or what it's called, I can check names and know what it's called and subset accordingly. And this is really the travesty of this class period. Data frames are lists. Data frames are lists of equal length vectors. And I've been lying this whole time. What's really going on is that when you look at like the structure of the cars data set, you'll note that it has the exact same structure output as a list. Here, data frames kind of in air quotes because data frames are lists. You'll see that the extract format here for our speed and distance variables are the same, and that it notes that the objects themselves are numeric because it can accept vectors of different types. Or if you take the length of a data frame, what you'll get are the number of elements like it's a list. You'll get the number of columns. Contrast this with getting the length of something that you've extracted from your list, like cars, extract this, and you'll see that it's got 50 rows. This is the same as 50 elements of a vector. But the funny thing is that you can also treat data frames like a matrix. You could say, for instance, cars subset 1, comma, nothing, and it'll provide to you just the first row. Or you could say cars 1 to 5, the speed column, and drop equals false, and it will return to you the first 5 rows of just the speed column as if you were subsetting a matrix with named columns. Okay. Question. Did I skip a slide? I did. No, you're good. Okay, so in classic R, let's say we wanted to get the average of the education column of Swiss for all of the rows that are above the average. This is how we would write this. We would say, can I get the mean of the Swiss data set subset to the rows for which the Swiss data education column is greater than the mean of that vector? That's for to subset the rows, and then give me just the education column, right? We contrast this with dplyr, which can provide us the same thing by saying Swiss and then filter education that's greater than mean education, and then summarize mean equals mean education. I feel like one of the reasons I like to teach dplyr is because of how legible this is to me. But one thing that you'll note as you get into R and get stronger at your coding skills and encounter more data sets and weird problems and social science, validity issues, what have you, you will also get way better at reading this for what it is and using it, because sometimes you'll have to. And sometimes the first time that you'll encounter a problem, you'll think of the answer in this syntax before this one. And so I say that part of the data structures lecture is to help get you on the track to thinking about the problems from both directions. Question? That provides just the education column from the Swiss data set that's called right here. Because the Swiss data set is a data frame and therefore can act like a matrix, and you can subset by column names after a comma. Well, we're taking a mean of the whole thing, so it's just going to be a scalar at the end. But about dplyr, a little bit about tibbles. So tidyverse functions often use a type of data frame that's called a tibble. You can create them manually using the tibble function, just like you can use data.frame to make a data frame. Or you can convert existing data frames into tibbles using as_tibble. Tibbles tend to display better than data frames. They truncate output and include column types. They also do not convert strings to factors. The only reason I say that they don't convert strings to factors is that prior to R 4.0, that was the default. This is no longer the case. They got rid of that. So if you're running on an old R version because, I don't know, you really like some bioconductor package, note that your strings might get converted to factors. Anyways, because the tidyverse has abolished row names, tibbles don't have any ever. You can convert row names to columns using tibble from the tibble package, row names to column, or with row names equals argument in as_tibble. So to see what I'm talking about, you might remember in the first homework, some people asked me about this. You could say Swiss and then select the second and third columns and then give me the first 6 rows. And you'll see over here that the rows have names, which are the provinces in Switzerland. A lot of the logic of the tidyverse is that this is information that we want as a column. Why would I want this as the name of a row when it could just be its own vector? And so here, to show you how you would get that to be its own column, you could say Swiss and then select the second and third columns and then as.tibble row names, and then you get to name it whatever you'd like. So I said name, and then give me the first 6 rows. And we'll see now that this is its own column. Question?
Is there an easy way to prevent art from cutting off trailing zeros? Like that 17?
It's not super easy depending on what the column is like, because you could look into the format functions and you could do like a across, like mutate across where is dot numeric tilde format, and you could get rid of those kinds of things. I want to provide an aside for some people with statistics training. If you don't have any statistics training, I don't know, check on the Braves game. So I want to talk about getting fitted regression coefficients. Recall that my list, the third element of it, is an output from a regression model. So we could say my list, double brackets 3 to get that third element, and then double brackets again to get just the coefficients. Okay. And then let's say we wanted just the coefficient for the speed covariate. We could say our speed beta object, assign it my list, the third element of my list, the coefficients element of that object, and then the speed element of that coefficients object that's here. What I want to highlight here is that you can chain subsets together and that things aren't too far away. Like whenever you have an R object, you can call any of the elements out of it. It might be in an unintuitive way to you at first. It might take subset chains like this, but it can be done. I know that with a lot of coding languages, especially in statistical software, sometimes doing something like this is something that you cannot do. It's hard to get just the beta that I'm interested in, for instance. The object that you get out of a regression, you often want to put it inside of summary. This will provide you with a list with more information, but it has the side effect of printing some output to the console. So often this is kind of what we're used to seeing in really boring papers, is this kind of output. I want to highlight that this is how you would want to get that information out. And let's say we wanted to get the standard errors from our summary output, because here these values seem very far away. I can't put these in an inline R code, for instance, because they come out as this object. So let's say we could do summary, my list, the element 3, and then we can subset straight from the summary. And this will provide us with a matrix of our coefficients. And then we could also chain these to say we want speed, the speed row from here, and the standard error column. So this is how you would try to get that explicit standard error straight from your summary output if you really wanted to grab it from this place. An example of why we'd want to do that is, let's say we want to conduct a 95% confidence interval using our speed standard error. So let's make an object called speed underscore CI, and we'll assign it that speed beta that we got out by chaining all of those subsets together. And then we add a vector that has it takes from the normal distribution a negative 0.975 and a positive 0.975. These are just the number 1.96, but I want to be able to motivate to you that you can ask for draws right from the normal distribution if you'd like. And then we want to multiply that by speed. So here we're doing a element-wise vector multiplication to multiply our standard error times negative 1.96 and positive 1.96. And then we'll name these rows lower and upper. And now you can include these values in an R Markdown document. So you could say a 1 mile per hour increase in speed is associated with R round the speed beta 1, feet increase in stopping distance, 95% confidence interval with our inline R code for our confidence intervals, and it will show up as a 1 mile per hour speed increase in speed is associated with a 3.9 foot increase in stopping distance. 95% confidence interval is 3.1 and 4.7. And then now, if you'd like to, go back and manipulate your data some way, it would still give you the correct confidence intervals in your R Markdown document at the end. Okay, people who are checking the Braves game, you can go back. A little bit about practice, about data structures and homework. So a suggested practice that I'm not going to take up, it's only for your own use if you have some extra time whenever you feel like it. There's a package called Swirl. You can do interactive R tutorials in the Swirl package that covers these structure basics that I've started today. To set up Swirl, you install .packages Swirl, load library swirl, and then run the command swirl. From there, you're going to choose our programming and pick a tutorial and follow the directions. To get out of swirl, you can type the function by, BYE, in the middle of the lesson, or select 0 in the menus. At this point, I'd say if you're new to R, that tutorials 1 through 8 are appropriate practice. They are kind of lengthy. I did them. They're neat. It's been some years, but I'm sure I carry that information with me. Also, there's a package called Learner, which you might want to try if you're interested in learning more about how RStudio works. I haven't used it myself, but if you're interested, just let me know and I can make it work. Okay, about the homework. There are 2 choices for homework this week. You only need to do one. This is the only week where it's going to be like this, where one's like the easier homework and one's the more difficult homework. The less advanced homework is data structure practice, where you will fill in a template or markdown file that walks you through creating, accessing, and manipulating R data structures. Enter values in the R markdown document and knit the document to check your answers. So the document checks your answers for you. And you can see the code there on how it does that. But every once in a while, somebody comes up with a type of error that was not anticipated by the markdown. Let me know if that happens to you. I'm very excited to know. Also, knit after each answer. It'll break if you don't knit after every answer that you fill out. If you get an error, check to see if undoing your last edit solves the problem. This will solve 99% of the problems. Coding an assignment to handle all possible mistakes is really hard. This assignment is also long in that it's not super difficult as far as difficulty, but it is pretty time consuming, so start early. This is also the first week in lab where I will just be walking through the homework step by step from start to finish. I will only be doing the less advanced homework in the lab. And I will be recording labs starting from then. The more advanced homework is manually doing a linear regression. For this, you will need to fill in a template or markdown file that walks you through 1, doing a linear regression manually, and 2, comparing it to the built-in LM function. This includes simulating your data and creating and modifying data structures. Also, knit after entering each answer, or you might break the template. This assignment does not check your answers as you go. This one's also long, so also start early. Again, you only need to do 1. And also, I don't expect a ton from your peer reviews that week. But that's it for me. Do you have any questions?
Could you just open the template, download this page at work?
Sure. Let's So when you first get the template, you'll want to knit it immediately. And here it will describe all of the instructions. And you'll see that in each of the code chunks, it'll say create a vector with the numbers 1, 5, 3, 2, and 4. And the example is you'll write it like this. And then you do that for each of these vectors and integers and so on, and just keep knitting after each answer.
Where does it check it then?
That's what all of this stuff up here in the code is doing. So it self-checks what your answers are. So like for instance, use sequence to create a vector of 10 numbers evenly spaced. Sequence 0, 15. Length that out equals 10. I hope I can do the first question on the homework. Oh yeah, I didn't save it. Okay, because I didn't download it correctly, it's not going. But when you fill out an answer like this and then knit it, it'll tell you down here on the under how did you do, whether or not your answer was correct. And it goes like that for all of the rest of the homework.
So as a peer grader, we just kind of seeing for completion then?
As a peer grader, you see for completion and assess these questions down at the bottom that are, you just type in your answer rather than it checks them for you. But again, I'm not looking for a lot. If you just check it, I don't think you're going to get a 0.
It's advanced in terms of like stats, concepts, not like much more difficult coding, or it's also like.
It's also more difficult coding because it has to deal with things like transposing matrices and matrix multiplication and things. And being able to feel confident in your answers is already more complicated. Of course, take care. Sorry? Am I from the Midwest?
Yeah.